Why, hello. Today we're going to go on to section 16.8. This will be our last section in this chapter. We are skipping 16.9. It's impossible to cover everything that you would love to cover. If any of you are interested in doing the transformations like they do in 16.9, you're more than welcome to read the section. I consider 16.9 to be pretty much an advanced calculus topic, and so that's why we're skipping it. But if you ever get into a course, especially an engineering course, and you need something called the Jacobian, that will be in section 16.9. But we're going to end with 16.8. In 16.8, we're dealing with doing triple integrals using cylindrical and spherical coordinates. And so first of all, let's take a minute and review what we learned many weeks ago about cylindrical coordinates. Remember, with cylindrical coordinates, in the xy plane, you really have your polar coordinates r and theta. And so therefore, x is equal to r cosine theta, y is equal to r sine theta, and x squared plus y squared is equal to r squared. And then we have our height as z. So we have coordinates r, theta, and z. And if you think about it, if you have like a cylindrical object, looks like this maybe, and you wanted to find out its volume, you would take the area of its base times its height. Okay? And if we're in polar coordinates, we already learned that your delta A in polar coordinates, or your dA, is r dr d theta. That will give you your base. And if you want to multiply it by your height, you'd multiply by dz. And so therefore, in cylindrical coordinates, dv is equal to your r dr d theta times dz. So if I have some volume that I want to figure out, or I want to integrate over some volume, and it just cries out that I want to use cylindrical coordinates because the base is circular, okay, and maybe the height is not, okay, the height is going straight, but the base is circular. I can change my integration using this substitution, plugging r cosine theta in wherever I see x, r sine theta wherever I see y, grabbing whenever I have x squared plus y squared, replacing it with r squared, and then replacing my dv with r dz dr d theta. And of course, you do not have to go in this order. Usually you always do dz first, but you pick dr d theta or d theta dr, whatever's more comfortable. So you might want to save this formula sheet if you printed it out. So the first one I want to do is I want to evaluate, and again with this one we're going to do some of the integrations, but I don't think, if I do all of them, I think I'll put you to sleep after about a 2-hour video. So instead we'll go as far as we can. We'll do some, and then others, we won't do. In this one, we want to integrate x cubed plus xy squared dv, where e is the solid in the first octant, that means positive x, positive y, that lies beneath the paraboloid z equals 1 minus x squared minus y squared. It's always important for you to be able to visualize what your picture looks like. So let's draw it. First octant, x, y, and z are positive, and we're underneath the paraboloid z equals 1 minus x squared minus y squared. Okay, now what does that look like? Well, it's a down z, right? He's a down z. It's a paraboloid. It's going to be coming down like this. And if we worry about the part that's in the first octant, it'll look something like that. Notice this equation right here has z equal to 0. If you're on the xy plane, you have your z coordinate equal to 0. If I plug 0 up here, I get 0 equals 1. You can't see that. Oh, now you can. 1 minus x squared minus y squared, or x squared plus y squared equals 1. And so what is this section down here? What is this? That's a circle, isn't it? It's a circle of radius 1. Okay, so if I wanted to draw my base, what does my base look like? It might help to draw the base. Your base is a circle of radius 1. Okay, the radius is 1. Except we're in the first octant, which has x positive and y positive, so we're in just this region right here. Okay? All right, now we're going to pull these up in a minute, but let's go back and look at our integral that we want to do. The integral that I want to do, it's going to be a triple integral. All right, and notice with this, I can factor out x, and I didn't notice this the first time I did this problem. I can factor out x, and we'll write this as dv, because notice we're going to be using these substitutions here. Where I see x, I'll put r cosine theta. Where I see r, I'll put r sine theta. But always you want to grab, if you have x squared plus y squared, you can replace it with r squared. And so my integrand is going to become, where I see x, I put r cosine theta. Where I see x squared plus y squared, I put r squared. Where I see dv, I put r dz dr d theta. All that goes in for dv. And the reason is your dz stays as it is, and your dA, the area of the bottom, is r dr d theta. Now I have to figure out what my limits of integration are. Well, going back and looking at my picture, first of all, we pick an arbitrary point in our base and ask, what does z range from? Well, coming back to my arbitrary point in my base, my z is ranging from z equals 0 till I get to a point on the paraboloid, right? So I'm going from z equals 0, and I could write it as z equals 1 minus x squared minus y squared, except we want to have this in r's and thetas and z's, and I think most of you would see if I took the 1 minus, factored out the minus for that, right? Z equals 1 minus parentheses x squared plus y squared. We can replace the x squared plus y squared with r squared. And so my limits of integration are going to go from 0 to 1 minus r squared. Now notice, we have an r times an r squared times an r. So it's going to be an r to the 4th cosine theta, and then dz dr d theta. Now we have to figure out what these limits of integrations are. That's down at the base. Now, you could look at this as your base. I prefer to look at, I wrote the xy plane all by itself. What is my r ranging from? It's pretty darn obvious. R is ranging from, take an arbitrary spoke in that region. R is ranging from 0 to 1. And my theta is ranging from 0 to pi over 2. Okay. All right, now I think we will do this one. We can't do them all, but we will do this integral. So the first thing I'm going to do is I'm going to do the inner integral from 0 to 1 minus r squared of r to the 4th cosine theta dz. Okay, we're doing the inner one first, this one right here, or really all the way to here. And notice r and cosine theta are constants. So this is just going to give me r to the 4th cosine theta times z, and we're going to plug in z equals 0 to z equals 1 minus r squared, which gives me r to the 4th cosine theta times 1 minus r squared, and then we normally would go minus, but if you plug in 0, that's going to drop out. So therefore, this is equal to cosine theta times r to the 4th minus r to the 6th. Okay, and that's just my inner integral. Now, unfortunately, we have to do it 2 more times. Okay, so I take that, and my next integral, looking at it, it's going from 0 to 1. So we're going to integrate from 0 to 1 cosine theta r to the 4th minus r to the 6th dr. Okay, because I brought that down here, and I see I'm going from 0 to 1 dr. And in this particular one, looking at it, this gives me, cosine theta is a constant, so we can factor that out. And this gives me cosine theta times 1/5 r to the 5th minus 1/7 r to the 7th as we go from 0 to 1, which gives me cosine theta times 1/5 minus 1/7 minus 0. Okay, and if you do the fractions, you can write this as 7/35, and that is 5/35. So we get cosine theta times 2/35. Okay, now we take that and we do the last integral. And so we have 2/35, which I think I will just factor out. And then we're going from 0 to pi over 2 cosine theta d theta. We're doing the last one. And let's see, the function that I know that has an integral, a derivative of cosine is sine. And bring 2 over 35 along for the ride. And we're going from theta equals 0 to theta equals pi over 2. So this will equal 2 over 35 times sine of pi over 2 minus sine of 0, which gives me 2 over 35. Sine of pi over 2 is 1, sine of 0 is 0. So the final answer is 2 over 35. Okay, and again, we're not going to be able to do all of them. It's too much. If any of these you would like me to, post on Blackboard, though, I could. I can have Chris type them up and we can post. The Student Solutions Manual is very nice in your homework for you, always checking to see each step how your integration, because there's millions of places for you to mess. On your test, just write neatly and show all your work, because you drop one minus sign, you shouldn't lose minus 12 or whatever on the particular problem. Okay, let's look at this one. Find the volume of the solid that lies within both the cylinder, x squared plus y squared equals 1, and the sphere, x squared plus y squared plus z squared equals 4. This is sort of a cool problem. I like this one. So let's first draw the picture. I think I'll draw the cylinder in pencil first. Cylinder x squared plus y squared equals 1. You're going to draw the circle x squared plus y squared equals 1, circle of radius 0. And draw little parallels coming up in the z direction. And there's my cylinder that goes on forever in the z direction. We need to be inside the cylinder, but we also have to be inside the sphere. Now, what is the radius of this sphere? 2. All right. So it has a radius of 2. I'll make that be 2, that be 2. So the sphere comes all, it comes around, and you're going to go 2 back here, but you're coming around. There's your top. Okay, and then it comes, back down here, and I don't look like I have it, and comes around here. But we have to be inside both the cylinder and the sphere. So first you got to be inside the cylinder, but then the sphere's cutting you off right here. And then it's going, oh, it comes all the way down here. It's going to cut us off down here too. You see that? And so what's our base? Here's our base. Our base is the circle. You see, that's your base. And if you take a little point on the circle, you can look up, top of the sphere, look down, bottom of the sphere. You with that? Remember, whenever you find a base, your base, you have to be able to pick any point and be able to look up and get one curve, and look down and get the other curve. So we're going to have our base be x squared plus y squared equals 1. Our base, just in 2D, is the circle of radius 1. Okay. Notice if you take a little delta area here, and you make your little parallelepiped here, the volume of that little thing that I'm not drawing very well is the area of the base. The area down here is the same as the area here, times the height, which is the distance from here to here. Okay, and that'll give you your area. So, redrawing the picture, because I really messed it up there a little bit. Let me redraw it. You have this lovely little cylinder right here that goes forever up, and it goes down. All right, and I want to find, I have this sphere that's cutting it off, top and bottom. Okay, so that's like my rooftop. And so my base is this circle. And I always like to redraw my base. My base, we decided, was x squared plus y squared equals 1. Okay, so we are going to do a triple integral. Now, notice, since we just want to find the volume, what's my integrand of my triple integral? 1. And normally we go dv, but we just learned a few minutes ago that dv in cylindrical coordinates are r, dr, d theta, and then dz. And you just put them in the order that you want. So I think I'll do dz first. So I'll go r, dz, dr, d theta. I'll do z first. Okay, now let's see. We got to find out if I take an arbitrary point, z is ranging from z on the bottom to z on the top. Okay, so let's go back and look at the equation. The equation for the cylinder was x squared plus y squared plus z squared is 4. I've got to get an equation for z on the top and z on the bottom. Well, notice if I solve for z, I got z squared equals 4 minus x squared minus y squared. Now remember, in polars, x squared plus y squared is r squared. So I can write this as z squared equals 4 minus quantity x squared plus y squared. And in polar coordinates, that gives me z squared is 4 minus r squared. right? And if I solve for z, z is plus or minus the square root of 4 minus r squared. Are we all comfortable with that? So coming back to my integral, we want to know what's z on the top. Well, z on the bottom is going to be minus square root of 4 minus r squared, and z on the top is plus square root of 1 minus r squared. Okay, you all with me? Question?
Could you go from 0 to square root of 1 minus r squared and multiply by 3?
Absolutely. This picture is beautifully symmetric, so you could go from 0 to square root of 1 minus r squared and then just double that volume. If you know you have symmetry in your volume, absolutely, you could do that. Okay, another question.
One on the top's wrong. 1 minus r squared? 4.
Oh, 4. Okay, thank you. That's a 4. All right, now looking at our little r d theta, which was our base right here, we say to ourselves, okay, what's r ranging from? Piece of cake, 0 to 1. And what is my theta's running from? From 0 to 2 pi. Okay, well, I think we will do this one, because this one I just want to show you the beauty of the cylindricals, because a lot of times this happens. If I do that inner integral, which I'm going from minus square root of 4 minus r squared, square root of 4 minus r squared, r dz. Since r is being considered a constant, this is going to equal r times z as we go from z equals minus that square root to plus that square root. And if you plug in that z, you have square root of 4 minus r squared minus a minus square root of 4 minus r squared, which just gives me r times 2 square root of 4 minus r squared, which I think we'll write as 2r square root of 4 minus r squared. So that's our first integration. I take that, and I'm going to write that as square root of 4 minus r squared times 2r. If that's okay with you. And our second integration is going from 0 to 1 dr. Well, the beauty of this we need to do a little u substitution here. My u is going to be 4 minus r squared, so du is minus 2r dr. So if you multiply through by a negative, minus du is 2r dr. And so therefore this becomes the integral from 0 to 1 of u to the 1/2 minus du, which, let's see, would be minus, increase your exponent by 1, dividing by 2/3 is the same, dividing by 3/2 is the same as multiplying by 2/3, which is going to give me minus 2/3 times u is 4 minus r squared to the 3/2. And we're going from r equals 0 to r equals 1, which is going to give me minus 2/3 times, you put in 1 here, 4 minus 1 is 3, so it's 3 to the 3/2, minus you put in a 0, 4 to the 3/2 is, the half says take the square root is 2, cube it gives me 8. And do you mind, I'm just going to write this as 2/3 times 8 minus 3 to the 3/2. Because if I just bring that minus inside, you get minus 3 to the 3/2 plus 8, which looks prettier this way. Now that's just a plain old everyday number. You know, that's just a plain old everyday number. So when I go to do my last integral, that's just a constant we can bring out front. Okay, and I have d theta from 0 to 2 pi. And so that's just going to be equal to 2/3 8 minus 3 to the 3/2 theta as we go from 0 to 2 pi. And that's just going to give us 2 pi. Which I could write as 4 pi over 3 times 8 minus 3 to the 3/2. And the point was this. What was so nice about this integration was when you look at the first integral, which I think I have right here, all right, and you end up with that square root of 4 minus r squared. The beauty was when you did that first integration, you ended up with an r here to help you with the square root. So the simple u substitution came out nicely. Okay, let's move on. I think we're going to have to slow down in terms of doing out every single one. Evaluate the integral by changing to cylindrical coordinates. Okay, we're just going to change, but we're not going to go through and do all the integration. Yeah, there's no big pitfalls in this particular one for me to talk about. Okay, now You look at this integration and you go, oh my goodness, can you imagine doing this? X, Y, Z, and then look what you're going from this to this, and then your X's is going from this to this, and then your Y is going from this to this. It would be nice to draw the picture of what this looks like. Okay? So first of all, if we change the cylindrical coordinates, remember, you're changing X into R cosine theta, Y into R sine theta, okay? Z remains as Z, and your dV, which was dz dx dy, becomes r dz dr d theta. But now next, before I do anything, I'll do all that. And also don't forget x squared plus y squared can very quickly be changed to r squared. We have to know what this looks like. What are they integrating over? Okay? So let's get a picture first before we do anything else. With this one, notice the inner integral has z ranging from z equals x squared plus y squared to z equals square root of x squared plus y squared. Right? That's what z is ranging from. So I have to know what those things look like. Well, what does z equals x squared plus y squared look like? This is your lower guy. You're going from this to your higher guy. What's z equals x squared plus y squared look like? Paraboloid, right? If you slice it with the y-axis, it's z equals x squared. You slice it with x equals 0, you get z equals x squared. You got a paraboloid. That's your lower guy. What's your upper guy? Your upper guy is z equals square root of x squared plus y squared. To help, square both sides. Maybe it would help if I did this. What's that a graph of? A cone. Remember when you have 0 here and you've got 1 plus and 2 minuses? And it could be 1 minus and 2 pluses, because if you multiply through by a negative, you're going to get the same, that same equation. When you get that equals 0 here, you've got a cone. The reason is, people, if I let y be 0, look what you get here. Z squared equals x squared. That's z equals plus or minus x. That's 2 straight lines. If you let x be 0, you get z squared equals y squared. You get z equals plus or minus y. You get another cone. So I'm going to have a cone. All right, now I just made it the positive part of the cone because it was z equals positive square root. Now notice our z's are ranging from the paraboloid to the cone. Paraboloid to the cone. You can sort of see you're getting that volume that's in between those. But now let's figure out what base we're integrating over down in the xy plane. Well, notice to get our base, let's look here. X is ranging from 0 to x equals square root of 1 minus y squared. X equals 0, I know where that is, right here. What does that look like? Let's square both sides. X squared equals 1 minus y squared, or x squared plus y squared equals 1. It's a stinking circle. Except our x's are only ranging from 0 to, notice it's the positive square root, so you're going this way to the circle. And then lastly, our y's are ranging from y equals 0 to y equals 1. Y equals 0 to y. So if I'm going from y equals 0 to y equals 1, this is the region. Okay, now we're ready to do our integration, to change our integration. So let's do it, and we'll bring these pictures out as we need it. It's going to be a triple integral. Where I see x, I put r cosine theta. Where I see y, I put r sine theta. Where I see z, I leave it as z. For dv, I use r dz dr d theta. Now we have to ask ourselves, can you see all that on the screen? Okay, pretty much. What is my z ranging from? Well, my z ranges from here to here. Now notice when I'm at the bottom, my z is x squared plus y squared. I'm on the paraboloid. But with polars, x squared plus y squared is r squared. So our lower limit of integration is going to be r squared. The higher point was the cone. With the cone, z is equal to square root of x squared plus y squared. X squared plus y squared is r squared. Square root of r squared is r. So my upper limit is r. For the base, dr d theta, it probably would be helpful just to look at this. If I'm doing r next, what's my r ranging from? From 0 to 1. And my spokes have my thetas going from 0 to pi over 2. And if you notice, if you look at this final integral, if I clean them up just a little bit, we're going from 0 pi over 2, 0 to 1, r squared to r. You have r times another r cubed z, dz, dr, d theta. And this is not hard at all to do. Okay, I'm not going to go through and do it. And I have the answer there. It turns out to be 1 over 96. Yes?
For the base circle, why just we take the quarter? Shouldn't it be half circle?
Say it again.
For the base?
Y is only ranging from 0 to 1. Notice your x is going from 0 to square root of 1 minus y squared. X is going from 0 to square root of 1 minus x squared, 1 minus y squared. That's positive. So this is just this side of the circle, just the positive side, positive x side. So we're only going this way, and then we're only including 0. Right, good point. Okay, now we got to go on to spherical coordinates. I thought of spending a lot of time developing the rules for the volume, but I decided not to. Let's just go down to the nitty-gritty. Remember, how do we do spherical coordinates? The way I think about it is if I have, this is hard to do in the TV studio, if this is my xy plane, my xy axis here, and I've got some z popping out right here, your phi that they talk about, your phi is, let me use a different color, the red guy. Phi is how much of an angle do you rotate from, think of it as due north, okay, this way, or this way, or this way. How much do you rotate from the positive z-axis downward? Notice phi is at a minimum 0, if you want to think in terms of degrees, 0 degrees or 0 radians. And you can rotate all the way down to the south pole, which would be pi radians, or 180 degrees. We use radians, all right? So that's what your phi is, how much you're rotating from the positive z-axis, from due north. Theta, we're drawing theta from the origin. But theta, if you think about it, you can have any little bar. You don't have to have your theta down here in the xy plane. You can have your bar up here, and let's pretend this is 0. We'll make this be 0 right here, all right? And it's how much do you have to rotate 0? You have to rotate your theta from 0 radians to get to, you follow on your level here. It's sort of like longitude and latitude. It's 0, and it doesn't have, you don't have to have your little thing emanating from the xy plane. You just have to be perpendicular to the z-axis up here. How much, like if I'm going to rotate from 0 degrees, which is positive x-axis, am I going to rotate, to pi over 2? Am I going to rotate to pi? Am I going to rotate to 3 pi over 2? All the way around to 2 pi to get to my point. So this guy's telling you how far you got to go in that direction. But notice your rho is how far you are from the origin. So you're coming along here, up along your phi to get your thing. And then theta is telling you how to rotate around this way to get where you want to be. From what we did last time, we noted that phi is always between 0 and pi. Also, if you notice, if you draw this parallel to this, here's a little right angle. The side opposite phi here is right here, and we know if you take the hypotenuse times the sine of the angle, it gives you the opposite side. So r is always equal to your rho times your sine phi. Okay, rho is right here. And this is the adjacent side, so z, because that distance from here to here is your z coordinate, is going to be equal to rho times cosine phi. So I have some of the formulas that we had from last time when we did cylindricals. And notice, you look at this and you go, who could ever remember this? But notice I just showed you that since r was equal to rho sine phi, this is saying x is equal to r cosine theta. You see, because r is equal to rho sine phi, so this is just a fancy way of saying r cosine theta, because this is your r right here. And y is equal to r sine theta. And this one, the reason z equals rho cosine phi is because this is the adjacent side right here. And if you have your angle and you have your hypotenuse, which is rho, the adjacent side is rho cosine phi. So that's where that came from. I'm not developing this. I'm just going to give it to you on a silver platter. I tried drawing pictures, and I can picture it, but in terms of drawing it for you guys, I really can't. So on a silver platter, we'll give you dV in cylindricals, I mean in sphericals, is rho squared sine phi d rho d theta d phi. And just to give you a little bit of a sense where that comes from, I really struggled with how I could draw this for you. If you look at, and I don't know if this is going to convince you or not, here's your phi, all right? Now notice that phi guy, you can move him this way. You with me? I can move him that way. If I move him this way or that way, this angle right here is delta phi. That distance is rho, and we know arc length is rho times delta phi. So that little piece right here, if I make my little phi a little bit more, a little bit less, I get rho times delta phi. Now, I told you theta we could draw like this, but we also could draw like this. Well, if theta, if I go a little bit more, a little bit less, remember this is r, which is rho sine phi. And if we go this much, if my angle right there is delta phi, this length right here is rho sine phi delta theta. So you can move this guy a little bit or that guy a little bit, or you can make rho a little bit deeper. You with me? Which would be delta rho. So if I take this length times this width times that depth, I get rho delta phi times rho sine phi delta theta times delta rho, and lo and behold, it's rho squared sine phi delta theta delta rho. And that's your delta V, is where it comes from. But drawing it is very hard 2D. I have something in my office that if you want to come, we can play with it. That's 3D that you can touch and hold. All right, so you want to have these written on your cheat sheet to help you, okay? But you also have to remember that phi is measured from the positive z-axis, and theta is how much you're rotating perpendicular to the z-axis from 0 degrees. Okay, let's do a couple. They're not all that hard. Evaluate the integral e to the x squared plus y squared plus z squared equals 3/2, where b is the unit ball, x squared plus y squared plus z squared is less than or equal to 1. Well, that's the inside of the sphere. We're doing the inside of the sphere. You're having a radius of 1. We can go up. We can go down. And the ball is edge is x squared plus y squared plus z squared equals 1. Now people, notice here, x squared plus y squared plus z squared is rho squared. So this is another way of saying rho squared is 1. Okay? Or rho is 1. The distance that you are from the origin for every point on the sphere is going to have a distance of 1 unit, because the radius of my sphere is 1. Changing this into spherical coordinates, I have e to the x squared plus y squared plus z squared. X squared plus y squared plus z squared is rho squared. So I can replace x squared plus y squared plus z squared with rho squared. Okay, and dv is rho squared sine phi. I'm just getting it from right here. And we can go d rho, d theta, d phi. Now, cleaning this up just a little bit, e to the rho squared to the 3/2. Well, when you go to a power, you multiply your powers together, so that would give me e to the third, e to the rho cubed, excuse me. And then I have rho squared sine phi, d rho, d theta, whoops, d phi. Okay, now we got to put what these limits of integration are. So let's go back and look at our picture. Now remember, rho is how far you are from the origin. So if I take an arbitrary spoke from the origin, I'm going to go from a distance of 0 to a distance of 1. Piece of cake. Now, I chose to do d theta next. D theta is the angle that you make with the positive x-axis. Or you could go look at your base if you want. But look, here's your base. Here's theta equal, this is positive x-axis, so here is theta equals 0. And as you can see, he's got to rotate all the way around. Do you see that? back to 2 pi. So theta is going from 0 to 2 pi. Now, phi goes from 0 to 1, 0 to pi. I'll do phi here. Here's phi equals 0, and to get all the way down to the bottom here, I've got to go all the way around, don't I? Till I get to pi, to get to the bottom half. And that's what your limits of integration are. This is not a hard one to do. For heaven's sake, this is an e to the u du right off. Do you see that? You got an e to the u du? So I'm not going to go do it. You guys can practice. You get a weird answer. It's 4/3 pi times e to the minus 1. Okay? The most important thing is practicing setting them up right now. Let's do another one. With this one, evaluate the integral z dv, where e lies between the spheres x squared plus y squared equals 1 and x squared plus y squared plus z squared equals 4. Okay, now, again, notice z is rho cosine phi. So where I see z, I'm going to put rho cosine phi. Okay, we all doing okay there? Okay. Then, what are we going to replace dv with? Well, dv I have right here is rho squared sine phi d rho d theta d phi. Okay, now I need to draw the picture, I guess, so let's draw it. Now, what are we doing here? We are in the first octant. Now, normally, a sphere, I would draw the whole thing, but the first sphere has a radius of 1, so he has a radius of 1. And we can bring him around like this. And this is a radius of 1, so we can go to this distance 1, that distance 1, that distance 1, and I guess it'd be nice to have, swing that around a little bit. Okay, that looks good. Okay, the other one has a radius of 2. 2. Oh, but we only want, excuse me, we only want the first octant part. So think of it as like you're coring an apple. You with me? Radius 2, and we want the part that's between both of them. You see that? Let's take an arbitrary spoke. If I take an arbitrary spoke, what is rho ranging from inside the region? 1 to 2. Rho is ranging from 1 to 2. Now, to get all these points in the picture, theta equals 0 is like this, and we have to rotate him around till he ends up right here, right? Theta equals pi over 2. Okay, and lastly now, this is theta equals phi equals 0. I need that, and I've got to rotate him all the way down until I get to the xy plane, right? And that would be theta phi equals pi over 2. Okay, now in this particular one, I'm looking at what I did. There, you know, the hardest part probably is I do end up with an integral. I have it somewhere along the line. You get an integral that is sine phi cosine phi d phi. That's the hardest part in all your integration. How do you do that integral? U substitution. What are you going to let u be? You let u be sine phi, then du is cosine phi d phi, and this becomes an integral of u du, which is blah, blah, blah. You can finish it. Okay? Okay, so I'm not going to finish it. We're going to end up, if we do it, 15 pi over 16. Most important thing is for us to see how to set these up. Let's do this one. Evaluate x squared plus y squared. Notice all our regions are spherical. You don't use spherical coordinates if your regions are not spherical. You'll use something else, okay? If they're cylindrical, I guess we're going to use cylindrical coordinates. All right, now this one. Evaluate x squared plus y squared dv, okay, where h is the hemispherical region that lies above the xy plane and below the spheres. So I think you can sketch this pretty easily, can't you? X squared plus y squared plus z squared is the sphere of radius 1. But this time we want the whole darn thing. My picture's not too good. And all the way down too. Okay. So popping this in, let's see now. X squared plus y squared is, what's x squared plus y squared? X squared plus y squared is r squared. Look in here. R is rho sine phi. So that's going to be rho sine phi squared. Do you see what I'm doing? Because I have here x squared plus y squared, and I know x squared plus y squared is r squared. Looking at my little cheat sheet though, r is rho sine phi. So there'll be rho sine phi squared, or x squared plus y squared is rho squared sine squared phi. You got to be real careful you don't get your phi's and your thetas confused. All right, so for x squared plus y squared, I'm going to put rho squared sine squared phi. Then for dv, I'm going to replace dv with rho squared sine phi d rho d theta d phi. And notice this becomes rho squared times rho squared is rho to the 4th. Sine squared times sine is sine cubed. And then we have d rho, d theta, d phi. Okay. Now with this one, let's go back and look at our circle, or at our sphere. Take an arbitrary spoke in the region. What is your rho ranging from? Piece of cake, 0 to 1. If I want to get the whole darn sphere, I start out at theta equals 0. Remember, theta emanates, you can draw him like this. He has to go all the way around, doesn't he? So theta is going from 0 to 2 pi. And now phi starts up here at the North Pole. All right, and he says, which way do you have to rotate down, 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 till you get to pi to get the whole sphere. Again, I'm not going to do this integration, except I'm looking at when I did it. And when I did it, the only problem, I mean, because, you know, I think all of us know how to integrate like rho to the 4th d rho. I think we're okay with that. Phi only goes from 0 to pi. It goes from, when we talk about phi, when you look at it, it's the angle that you make coming from 0, North Pole, down. The most he can go is all the way down. Because then you know you use theta then to swing it to get to where you want to be in which quadrant. Okay, now, say this again.
It says above the xy.
Oh, let me see. Oh, it does. The hemispherical region above the xy plane. So if I'm above the xy plane, I just want the hemisphere. And of course, it does say hemisphere. I apologize. And so your phi would just go from 0 to, that's why we have students in the audience. There you go, 0 to pi over 2. I apologize. Instead of getting 4 pi over 15 for the answer, my integral would have given you 8 pi over 15 because the volume of the, oh, in fact, yeah, because this is beautifully symmetric, so I would be okay.
Would that change the range for?
For theta? No, because theta is, look at, you're going all the way around. Here's theta equals 0. You got to go to theta equals pi over 2. Theta equals pi. You got to swing all the way around. Okay, because if you think about it, your base, if you draw the base of that, it looks like that. Okay, it's the same theta that you have. The theta in spherical is the same theta as you have in polar. When I did this integration, I was like, where's pitfalls, where are because the hard part about Calc 3 is remembering how to do the integrations. There is an integral that you get to a certain point where you have the integral of sine cubed phi d theta, though that's not a problem. You go through, no, forget about that. You get an integral where you have sine cubed phi d phi is what you have at a certain point. How do I integrate sine cubed phi d phi? You remember that you can replace this as sine squared phi times sine phi d phi. And you replace sine squared with 1 minus cosine squared. And then what's u going to be? U is going to be cosine. And du is going to be minus sine. That's a phi. So minus du is sine phi d phi. And so therefore this integral becomes 1 minus u squared, and for sine phi d phi we put in minus du. And you guys can continue from there, okay? And what, you know, if your time is short, some of the things that I can't finish, if I were you, you print these out and use those as your exercises for starters. I mean, that's a wonderful thing, and then you can go back and see, oh yeah, how do I set it up, and then how do I integrate it? Also, if time is short, I have no problem with all the other ones, setting them up and then opening the Student Solutions Manual and seeing, you know, and then you might want to look to see, you know, where's the hairy parts, you know, where am I going to be struggling with my integrations. Okay, a few more things I want to do. The last 4 that we're going to do. The directions say sketch the solid whose volume is given by the integral and then evaluate the integral. We're not going to do the evaluate part. Okay, you can do that for homework. And I do have the answers there. But I think it's very important to be able, if an integration is set up, to be able to picture what it looks like. All right, so let's do this one. This one, let's looking at it. The first one that we want to do, what is z ranging from? First of all, what kind of coordinates am I using? I'm using cylindrical because it goes dz, d theta, dr. And I look and I say, what is z ranging from? Z's ranging from z equals r to z equals 4. I know what z equals 4 looks like. That's a plane. That's a horizontal plane, okay? Sort of like you can think of it as a magic carpet, right? Floating 4 units above the xy. This one's not as obvious to me, but remember, in polars, r squared is x squared plus y squared. And so this is z equals the square root of x squared plus y squared. Or z squared is x squared plus y squared. What's that a graph of? We've done it a million times today, or at least twice. It's a cone, right? If you want to, you could go 0 equals x squared plus y squared minus z squared. When you have x squared, y squared, z squared, and just one guy is the odd man out, and you have equals 0, you've got yourself a cone. The reason is, if you look up here, z squared equals x squared, make y be 0. Z is plus or minus x. Those are nice, sharp, straight lines. Z equals plus or minus y. Nice, straight, sharp lines. So drawing that so far, what do I have? I have a cone. And then I'm chopping it off with my magic carpet, z equals 4 at the top. Because my z is going from the cone to the top, z equals 4. All right, now let's look at what our base is. Well, our base, we can do right here. They have theta going from 0 to 2 pi, and they have r going from 0 to 4. Well, I think I can draw that in the xy plane. What do you think that looks like it's going to be?
Circle.
Oh, definitely, it's a circle. It's a circle. Theta is going from 0 to 4, and then r is going from 0 to 4, and then you're getting all the way around, and you're getting the whole darn circle. And in fact, you can see here, this is your base. If you take the image of that, the shadow of that onto the xy plane, you're getting this lovely circle of radius 4. So what are we integrating? What volume are we finding? We're finding the inside of this cone right here. Okay, let's do another one. Next one, and by the way, I have the answer there. It turns out to be 64 pi over 3 if you do the integration. But looking at it, I don't see anything that's, it's really easy to drop a square here or a cube there, but nothing that's rocket science. This one, this is in cylindrical, right? Cylindrical. First of all, z is ranging from z equals 0 to z equals 9 minus r squared. Z equals 0, I know what that is, the xy plane. R squared, remember, is x squared plus y squared. What does z equals 9 minus x squared minus y squared look like? Hyperboloid. That's a hyperboloid. It's an upside down hyperboloid that's hitting 9 for the top, right? So here's my hyperboloid. Okay, I think that's good enough. Okay. By the way, what's the the hyperboloid's base? Looks like that. How can I find out what the equation of that base is? Well, if you're on the xy plane, what does z equal? 0. If you're on the xy plane, z is 0. So we have 0 equals 9 minus, oops, 0 equals 9 minus x squared minus y squared, or x squared plus y squared equals 9. So that base is a circle of radius 3. Okay, now we got to look at what their other integrations are from, though. Looking at the other integrations, we have r ranging from 0 to 2, and theta ranging from 0 to pi over 2. If theta is just going from 0 to pi over 2, you're going to stop right there, aren't you? And r is only going from 0 to 2. That's your base. And therefore, this is your height. And so if we go up here, you see that this is, when you go up here, it's going to hit it to a certain point. Maybe it's like right here. And then this is the region that we're integrating over. You see that? Because your base goes from 0 to 2, and then from 0 to pi over 2. And I'm thinking, if this is my base, and I bring perpendicular straight up to the sphere, bring the perpendicular up at 2, it's not going to go all the way up to here. It's going to go maybe to here. And this is only going to go to here. This circle is going to go about here. And then, since this is the xz plane, I'm going to have a wedge cut out here, a wedge come out there. Okay? Okay. So what you're doing is you're looking at the part of the sphere that is above this little wedge, this little circular section here, that little quarter of a circle. Okay, we've got 2 more to look at that are in cylindrical coordinates. Definitely this is in cylindrical, isn't it? Okay. What is rho ranging from? Believe me, I think spherical are the easiest. Rho is ranging from 0 to 3. Theta is ranging from 0 to pi over 2. And phi is ranging from 0 to pi over 6. Okay. Bringing that down. Okay, bringing that down here. Let's do the phi first. If phi, remember what phi is. Phi is the angle you're making with the z-axis, right? Let me make this on a little piece of paper here first. If this is your xy axis, and here's your north pole, phi, this is at phi equal to 0. Pi over 6 is how many degrees? 30. So you can rotate down to 30 degrees. But remember, you can swing it. You can rotate 30 this way. You can rotate 30 this way. You can rotate 30 this way. You follow? I can go from here to pi over 6. 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 What am I getting? I'm getting a cone. Very good. So looking at phi, phi's the kings of the kingdom, we can go out a total of pi over 6. All right? Since rho is from 0 to 3, we can go from 0 all the way up to 3. 0 all the way up to 3. So we're getting a cone. Except theta only allows us to go from 0 to pi over 2. So what part of the cone are we getting? The part that's in the first quadrant. You're right. Right here. Can you see it? Because your theta is only going from 0 to pi over 2. So you're only getting the part of the cone. You know, you have like these sides here, that's my top, and it's just a quarter of the cone. And we're going up to a rho of equal to 3. Isn't that cool? Okay. Can I put these on the test? I don't know. It would be sort of hard to ask. I think I have matching. That would be cool. Okay, let's do this one before we call it quits. This one, rho, is ranging from 1 to 2. Phi is going from pi over 2 to pi. And theta is going from 0 to 2 pi. Okay? All right. Now, shall we try it? What does this phi going from pi over 2 to pi tell me? In the TV studio, it's tough in terms of how to draw it. if this is my XY plane and here is my Z axis, here's my XY plane. Here's my Z axis coming down. If you're above the XY plane, your angle is going to be from 0 to pi over 2. But if you're going from pi over 2 to pi, you're going below the XY plane, right? So what's happening is we're below ground here, right? Phi from pi over 2 to pi means we're below the XY plane. We're below. Okay, now rho is from 1 to 2. So the rho can go from 1 to 2. From 1 to 2. So here is a circle of radius 1. Here's a circle of radius 2. Here is my hemisphere. Okay, so we're going to be between rho equals 1 and rho equals 2. Okay, except theta goes from what? From 0 to 2 pi, so it goes all the way around, except we're going to take what part of it? What part of this hemisphere?
The lower part.
Right, we're taking the lower part. I don't really like my picture, so let me give me one more stab. Here's my inner circle of radius 1. Here's my outer circle of radius 2. We're taking everything between this little circle and this big circle, but we're just below the xy because phi is going from pi over 2 to pi. Okay, and then the integration's not all that big deal, so we don't need to play with that. Okay, for homework, I want you to read pages 1069 to 1073. Skip example 1. It's a density problem, and we didn't do the density functions. Then on 1073 to 1074, I have picked problems that are nice. Do you have the time to do all of them? You probably don't. You know, you've got to pick and choose what you have the time to do. Looking over them and trying to set them up, though, and then looking at the Student Solutions Manual might be a good thing to do, to go through and do all of them. And then pick and choose which ones you can practice doing the integrations. I want you to do 1 to 11 the odds, 7, 19, 21, and 33. You have a practice test, which has problems. Do you have time to write all those out? I doubt it. But you know which ones you're struggling with, and that gives you extra ones to do. Chapter review. Notice we're skipping 16:9. Chapter review, I want you to look at 1086 to 1087, numbers 3 to 31, the odds, and 39 to 41. Those of you that are home, if you have any that you don't understand, make a point of coming in to see me, or email me, or fax me, and I can help you with the ones you're struggling with. Good luck on your test, and I'll see you next time.